All right, hello everyone. Today we are going over lesson 5.5 and 5.6, which is on the collision model and potential energy diagrams. Let's go ahead and start out with our collision model. In this lesson, we're learning that reaction rate depends on particle collisions. So the faster and more efficient particles collide, the faster a reaction can happen. We know that not every collision is going to cause a reaction. For an elementary reaction to form products, particles need to collide with enough energy to overcome that activation energy and with the correct orientation so that bonds can break and new bonds can form. Since only a small fraction of collisions meet the requirements, most collisions are deemed unsuccessful. However, we can look at this with the Maxwell-Boltzmann distribution, which helps us visualize how many particles have enough energy to react, and it also shows that increasing temperature increases the fraction of successful collisions, which then speeds up the reaction. Collision theory explains that particles are constantly colliding, but only certain collisions actually cause a reaction. For a collision to be effective, particles must collide, have enough energy to meet or exceed the activation energy, and hit with the correct orientation so that bonds can break and new bonds can form. If the energy is too low or the orientation is wrong, that collision is going to be ineffective and the particles are simply going to bounce off one another and continue on their merry way. The reaction rate is basically a measure of how many successful collisions happen per second. So anything that increases successful collisions is going to increase our reaction rate. Like discussed in 5.1, there are factors that speed up reaction rate by increasing the number of successful collisions. The first one we're going to talk about today is surface area. So by breaking a solid into smaller pieces, we're going to increase the surface area, which exposes more particles and leads to more collisions. In a solution, if we increase the concentration, that puts more particles in the same volume, so more collisions are going to happen more often. And then for gases, if we increase the pressure, that forces particles to move closer since it's decreasing volume, which also increases collision frequency. And then we have temperature. Increasing temperature is going to increase our average kinetic energy. So particles are going to move faster and collide with more energy. So a larger number of collisions are going to overcome that activation energy and produce products. Given the following reaction, which set of reaction conditions will result in the highest reaction rate? Explain in terms of collision theory. So the first thing I notice is that all of my temperature values for all three experiments are the same, which means my average kinetic energy of my particles is not changing. They're all the same. So next, I want to look at what I'm given. I'm given moles of my reactants and I'm given volume. And I know that concentration is moles per unit of volume. So if I look at the concentration, I know that an increased amount of concentration will give me a higher rate because that means I have more particles in the same volume. So let's look at experiment 1 first. We have 2 total moles and a volume of 2 liters. Now looking at experiment 2, we have a total of 4 moles in 4 liters, which is again 1 molar. And then finally looking at reaction or experiment 3, we have a total of 2 moles in 1 liter of solution, so that is 2 molar concentration. So if we are looking for the conditions that will result in the highest reaction rate, we are going to want experiment number 3 because it has the highest concentration, which means particles are closer together and collide more often. So it's going to have the highest reaction rate. All right, moving on to an example FRQ. A student performs an investigation to study factors that affect the rate of reaction. In each trial, the student combines 15 milliliters of hydrochloric acid at 21.2 degrees Celsius with 1 gram of calcium carbonate and measures the time required for the reaction to go to completion. The data is given in the following table. Part B says the student correctly identifies that trial 5 is inconsistent with the other trials. Explain why the student's claim is correct using the data in the table. So in trial 5, we have 3 molar HCl with small chunks at 227 seconds for the reaction. So looking at my concentration, I'm going to start there because that's my first column. I have experiment 4, 5, and 6 having the same concentration. So I'm just going to compare particle size and time to make sure that all those kind of line up. So I know that my fine powder has the highest amount of surface area and my large chunks have the lowest amount of surface area. So these should go in order from smallest time of reaction to largest time of reaction, and that is not the case. You can see that trial number 5 goes a lot slower than trial number 6, which doesn't make a lot of sense because small chunks have more surface area than large chunks, which means that its time of reaction should be less than 114 and more than 22. So that would be the way that I explain it. You could also explain it by comparing it to the other experiment with small chunks that is also part of the rubric. All right, then another part of that same FRQ says based on the reaction conditions and the collisions that occur between particles, explain the reason for the difference in reaction times for trial 2 and trial 3. So we can see the main difference with trial 2 and trial 3 is the particle size. So trial 2 has small chunks and trial 3 has large chunk, which means the small chunks have more surface area and the large chunk has less surface area. So it makes sense that the large chunk takes a lot more time to react because it has a much lower surface area, which means less particles are reacting. The Maxwell-Boltzmann distribution shows that particles in a sample do not all have the same energy. Instead, their energies are spread out across a range. So on the graph, the area under the curve represents the total number of particles, and that total stays the same even if conditions change. The vertical line labeled EA represents the activation energy, and only the particles with energies to the right of EA have enough energy to react during a collision. Changing reaction conditions, especially temperature, changes the shape of the distribution and affects how many particles have enough energy to produce successful collisions. This Maxwell-Boltzmann graph shows how particle energies are spread out across a range. The peak represents the most probable energy, and the dashed line shows the average or mean energy. We already went over the activation energy line, which showcases the minimum energy needed for a collision to produce a reaction. Only that small shaded region to the right of the activation energy represents the particles that have enough energy to react, while, as you can see, the majority of the particles to the left do not have enough energy. That reaction rate is going to specifically depend on how many particles fall into that tiny high energy region, because those are the ones that actually can create successful collisions. Increasing temperature shifts the Maxwell-Boltzmann distribution to the right, meaning more particles have higher kinetic energy. This causes collisions to happen more often, and more importantly, a larger fractions of collisions are successful because more of them have energy that are equal to or greater than the activation energy. Since the reaction rate depends on the number of successful collisions per second, raising that temperature is going to increase the overall reaction rate. Adding a catalyst does not change the shape of the Maxwell-Boltzmann energy distribution because the particles' energies are staying spread out the same way at the same temperature. However, the catalyst is going to provide an alternate pathway with a lower activation energy. So that activation energy line is going to shift to the left, which means a larger fraction of particles now have enough energy to react, which leads to more successful collisions and then increases the rate. So this example compares Maxwell-Boltzmann curves at 3 different temperatures to show how temperature affects the number of particles with enough energy to react. So at a low temperature, 100 Kelvin, most particles have a low speed and a low kinetic energy. So only a tiny fraction can reach the activation energy. As temperature increases to 200 Kelvin and then to 400 Kelvin, the curve spreads out and shifts to the right, which means more particles have a higher energy, and a large portion of the curve would be beyond the activation energy. So a low activation energy line would be drawn further left, so many particles at all temperatures could react, while a high activation energy line is going to be drawn further to the right, meaning only the highest energy particles, especially at high temperatures, would be able to react. The diagram above shows the distribution of molecular collision energies for equimolar samples of a reactant at different temperatures. Based on the diagram, at which temperature will the reactant be consumed at the fastest rate and why? So remember when we're talking about rate and then we're looking at Maxwell-Boltzmann distributions, we want to look for the greatest number of particles to the right of the activation energy line. And as you can see, our T4 curve is going to create the most amount of particles on the right side of that activation energy, which means if we have more particles that have enough energy to overcome that activation energy barrier, that means we're going to have more successful collisions and a higher rate. All right, so now let's move on to lesson 5.6. In this lesson, the focus shifts to using a reaction energy profile to show what happens energetically during elementary reactions. So during a reaction, bonds must be broken and formed, and that requires an input of energy to reach the transition state. So the reaction coordinate is going to represent the pathway the reactants follow as they rearrange into products. And the energy profile is going to track how potential energy changes along that pathway. Potential energy diagrams help compare exothermic and endothermic reactions by showing the energy of the reactants and products during reaction progress. So I know we already went over this, but just make sure that you can look at these energy profile diagrams and be able to quickly determine if it's exothermic and endothermic. A very simple way to think about it is exothermic reactions are releasing energy, so we should be going down in energy. So as you can see on the left one, we are going from this energy down to this energy, which means we have a negative delta H, or a loss of energy. And then with our endothermic reactions, we are gaining energy. So our products will have more energy than our reactants. 4 main parts of the reaction coordinate that you just have to keep in mind. Number 1, the reactants. They'll always be in the very left of the PE graph because the x-axis is going to represent progress of the reaction. Our activated complex is the peak of the graph. That is going to be the highest energy and the most unstable point of the reaction. Our products are always the plateau at the end or to the right of the graph. And then our activation energy is the energy required to break bonds in a reaction to go from the reactants to the activated complex, which eventually then goes to our products. All right, and I know we already did this in a previous video, but I'm just going to remind you, whenever you add a catalyst and you're showing it on a energy profile diagram, remember you are not changing your enthalpy or your delta H. You are not changing your energy of your reactants or your products. all you are changing is your activation energy. So you're just going to draw a curve with a lower activation energy. Everything else is going to remain the same. An energy profile diagram can represent a reaction mechanism by showing the energy changes for each elementary step. So each peak on the graph is going to represent one step, and the highest point of each peak is known as the activated complex. The valley that is in between the peaks is going to represent our intermediate, which is formed in one step and used up in a later step. And the step with the largest activation energy is going to be our rate determining step or the slower step. And that's because it is the hardest energy barrier to overcome. And even if the reaction has multiple steps, remember the overall delta H is going to depend on the energy difference between the reactants and the products, not on how many steps occur in between. Now, looking at this diagram on the right here, you should be able to identify that there are two elementary steps, and that our first elementary step is going to be the rate determining step because the activation energy is much greater than in the second elementary step. And the other thing I want you to be able to identify is that here is where your intermediate will be formed. All right, so this free response question says NO2 and F2 can react to produce NO2F as represented above. A proposed mechanism for the reaction has two elementary steps as shown below. Write a rate law for the overall reaction that is consistent with the proposed mechanism. So we remember that rate law with elementary steps is going to be based off of our rate determining step, which is the slow one. So since the slow step is our first step, we're just going to write rate is equal to K times the concentration of our reactants raised to the power of the coefficient, which is only 1. And this would be our rate law for this specific mechanism. On the incomplete reaction energy diagram below, draw a curve that shows the following two details: the relative activation energies of the two elementary steps and the enthalpy change of the overall reaction. So first, let's go ahead and focus on our elementary steps. We know that our first step is the rate determining step, so that means the first peak is going to have the highest activation energy. So I'm going to go ahead and draw my first elementary step, which has a pretty high activation energy. Then this valley here will be our intermediate. And then we're going to go ahead and draw another peak for our second elementary step, so that will have a much smaller activation energy. And then we're going to go ahead and draw our plateau for our products, and we just have to make sure that is lower than our reactants so that we can show the enthalpy change is negative as in the delta H. And that concludes our lesson on 5.5 and 5.6. If you have any questions, please feel free to leave a comment below, and I'm happy to get back to you on that. Have a great day. Bye.